Hello, everyone! You successfully made it through Part 1, where we tackled the introduction and covalent bonding, and you breezed right through Part 2 on the versatile nature of carbon and homologous series. So, a huge welcome to Part 3 of Class 10 Science, Chapter 4, Carbon and its Compounds. Today, we are setting the stage to really explore the chemical properties of carbon compounds. Let's get right into it.
Okay, let's dive into this. Have you ever stood in your kitchen, turned on the gas stove, and just wondered, how exactly does the LPG in that heavy cylinder burn and produce so much heat? It's a pretty fascinating everyday mystery, and it all comes straight down to carbon chemistry.
Or, consider this scenario. Why does alcohol completely change and turn into vinegar if it's just left open to the air? There are literally invisible chemical reactions happening right in our kitchens and dining rooms all the time, completely transforming the very substances we use every single day.
And here is one final question to ponder. How is soap actually different from detergent? Well, the answers to all these phenomena, the real magic behind these everyday occurrences, lie in the chemical properties of carbon compounds. And that is exactly what we are unpacking in today's explainer.
So, here is our roadmap for today. We'll start with those everyday carbon mysteries. Then, we'll look at combustion and energy. After that, we'll break down 3 key chemical reactions, followed by a close look at ethanol and ethanoic acid. And finally, we'll wrap up with a quick review and a question to test your knowledge.
Section 1. Everyday carbon mysteries.
Section 2. Combustion and energy.
So combustion basically just means burning. When most carbon compounds burn in the presence of oxygen, they undergo a reaction that produces 4 things: carbon dioxide, water, heat, and light. A classic, perfect example of this general equation in action is methane. When methane burns in oxygen, it undergoes this exact transformation. And what you'll always observe in these kinds of reactions is that the carbon compounds burn with a flame, and crucially, a massive amount of heat is produced.
Now, why are carbon compounds used so universally as fuels? Well, it's pretty simple. They produce large amounts of heat, they burn incredibly easily, and they are readily available to us. This is exactly why we rely heavily on substances like LPG, CNG, petrol, and diesel for virtually all of our everyday energy and transportation needs.
And this brilliantly illustrates a really crucial difference you need to know. Saturated hydrocarbons usually burn with a beautiful, clean blue flame, but unsaturated hydrocarbons, they burn with a yellow, sooty flame. Why is that? It's all because of incomplete combustion. So the next time you see a yellow, smoky flame, you'll know you are witnessing the incomplete combustion of an unsaturated carbon compound right before your eyes.
Section 3. 3 key chemical reactions.
All right, the first of these 3 essential reactions is oxidation. Oxidation is simply the process of adding oxygen or removing hydrogen. To make this happen, we use what are called oxidizing agents. Basically, these are just substances that step in to supply the needed oxygen. Excellent examples include alkaline potassium permanganate, that's KMNO4, and acidified potassium dichromate, which is K2CR2O7. A perfect example of this reaction is when ethanol changes into ethanoic acid thanks to the presence of one of these oxidizing agents.
And hey, this brings us right back to our second everyday mystery from the intro. Why exactly does alcohol turn into vinegar? Well, when fruit juice or alcohol is exposed to air for a long time, this exact oxidation process occurs naturally. Oxygen is added over time, and as a result, the taste and the smell completely change. Mystery solved.
Moving on, our second key reaction is the addition reaction. This occurs specifically in unsaturated hydrocarbons. Remember, those are the ones with double or triple bonds. In this reaction, hydrogen can be added straight across these bonds. For example, ethene reacts with hydrogen to form ethene. And to get this transformation to happen, it takes place in the presence of catalysts, which are typically metals like nickel, palladium, or platinum.
Now, a very specific and super important type of addition reaction is called hydration. This is simply the addition of hydrogen to unsaturated compounds. But why does this matter to us? Well, think about the food industry. Vegetable oils are naturally unsaturated. Through hydration, these liquid oils are converted into solid fats, like Vanaspati ghee. It's an absolutely critical process for modern food manufacturing.
Okay, the third key reaction is the substitution reaction. Unlike addition reactions, these occur in saturated hydrocarbons.
Because the compound is already totally saturated, we can't just squeeze in more atoms. Instead, one atom has to be replaced by another atom. It's basically a swap. A classic example is when methane reacts with chlorine in the presence of sunlight. One hydrogen atom in the methane is swapped out or substituted by a chlorine atom.
So, the crucial point is, if we compare these head-to-head, addition reactions occur in unsaturated compounds where atoms are just added right in, like with ethene. Meanwhile, substitution reactions occur in saturated compounds where atoms actually have to be replaced, like with methane. It's a fundamental difference in how these molecules behave.
Section 4. Ethanol and ethanoic acid.
Let's look at a couple of specific compounds now. First up is ethanol. Its chemical formula is C2H5OH. Ethanol is what is commonly known as alcohol. If you were to observe it, you'd see it's a completely colorless liquid, and it actually has a quite pleasant smell.
The impacts of ethanol are vast, and really, they are dual-sided. On one hand, it has incredible utility. It's widely used in medicines, acts as a really powerful solvent, goes into perfumes, and is used across all sorts of industries. However, it is equally important to note the other side. Excessive consumption of alcohol carries severe harmful effects. It negatively affects overall health, causes direct damage to the liver, and deeply impairs the nervous system.
Our second key compound is ethanoic acid, with the formula CH3COOH. You might know it better by its common name, acetic acid. Just like ethanol, it's a colorless liquid, but it has a very sharp, sour taste and a really distinct vinegar-like smell. In fact, what we commonly use in our homes as household vinegar is literally just a 5 to 8% solution of acetic acid.
Because of these highly practical properties, ethanoic acid is incredibly useful to us. It's an absolute staple for food preservation, it's the primary ingredient in manufacturing vinegar, and it's totally vital in the industrial production of various medicines and chemicals.
Section 5. Review and final question. Congratulations on navigating all this complex chemistry today. Just to do a rapid-fire recap, we unlocked the properties of carbon by studying combustion, the burning of fuels for energy. We looked at oxidation, which explains why our food and drinks change over time. We compared addition reactions, including hydrogenation, which gives us solid fats, right against substitution reactions in saturated compounds. Finally, we examined the everyday applications and the real-world impacts of ethanol and ethanoic acid. These 7 concepts are literally the foundation of carbon chemistry.
And now, to wrap things up, I want to leave you with one final provocative question to test your new knowledge. Think way back to our discussion on combustion and fuels earlier. Why do unsaturated hydrocarbons burn with a yellow flame? I highly encourage you to write your answer down in the comments section to see how well you've grasped today's concepts. Keep exploring, keep questioning, and I'll see you in the next explainer.